This video will take a look at the CPU in terms of its structure, its function, and its performance. So what is the purpose of the CPU? Well, from GCSE, you will know that the CPU is known as the brain of the computer, and its job is to process data. And when we're talking about processing, we're saying things like searching, sorting, calculating, and decision making. The CPU is at the heart of everything that goes on in the computer. Now, the fetch, decode, execute cycle are the three steps that the CPU will carry out in order to process data. So to begin with, when you open up a program, you double click on that icon on the desktop. When it's open, its data and instructions are loaded onto the RAM. As the RAM is accessed directly by the CPU can then get to work. So, the first stage is the fetch stage. In this stage, the CPU will fetch some data and some instructions from main memory, from the RAM, and then it will store it in its own temporary memory called registers. Now, the way in which it requests data is it asks for data by saying, I would like some data at a particular address. The RAM will then send that data back to the CPU. And it requests data and gets data delivered to it using buses. Now, the address bus is the first bus in this process. Now, the address of the next item that the CPU wants is put onto the address bus. So the CPU will say to the RAM, can I have the data or the instruction that is in address number, let's say 7. Then the RAM will retrieve that data from that particular address and will send it back to the CPU along the data bus. The CPU has now fetched that data. The next stage is the decode stage, and this is where the CPU will make sense of the instructions that it's fetched and know what to do with the data that it's got. So the CPU decodes the instruction and then gets things ready for the next step. And the next step is the execute stage. So the execute stage is where the processing actually takes place. The instructions that the CPU has been given is then carried out on the data. And then once that cycle is completed, another one begins. And that's the fetch, decode, execute cycle. So let's have a look at the CPU structure. We'll have a look at the fetch, decode, execute cycle in a bit more detail. We'll understand the structure and we'll understand exactly what's going on at a much higher level. So the CPU is made up of three parts. It's made up of the control unit, the ALU, which is the arithmetic logic unit, and the registers. So the control unit, now that controls the workings of the CPU and the von Neumann architecture. Now it coordinates the running of the processor, including the movement of data between components and decoding instructions. It does this using control signals. The ALU, that is responsible for the calculations and the decision making. And the registers is where data and instructions are queued up before they're going to be executed. Okay, so the CPU's own memory store, which is extremely quick, contains several specialized registers which are at the heart of the fetch, decode, execute cycle, and we will indeed have a look at that a little later on. Now, if it helps, you can think of the CPU's three main areas working together a little bit like an airport would work. You've got the control unit, which oversees the workings of the CPU, sends out all of those control signals. You can think of that as the control tower in an airport, looking over the airport, making sure that aeroplanes are queued up and only go onto the runway when it is safe to do so. You can think of the registers as the taxiways where all the planes sort of queue up, ready to get onto the runway. And you can think of the ALU as the runway itself. That's where the magic happens. That's where planes are taking off, planes are landing, and in this case that's where all the execution takes place of instructions and data. So the CPU buses. On this image that you can see that there are lines that are connecting the CPU with the main memory and with the input and output devices. Now the black line represents the control bus. Then you've got the sort of purple line, which is the address bus, and you've got the data bus, which is blue. Now we've already talked about these a little bit, but ultimately buses are just connections between these devices. They're a collection of wires and channels which allow data and instructions to be communicated between devices. Now the data bus, that's responsible for moving data between the CPU and the main memory and also the input and output devices, but it's data that goes along the data bus. The address bus communicates memory locations, so where the data is to be stored or where the data is to be retrieved, but it's addresses that move along the address bus. Don't get those confused, okay? Addresses on the address bus, data on the data bus. And the control bus, that is responsible for communicating those control signals, okay, to make sure that everything in the CPU works with or in a synchronized manner. So the control bus will send out control signals, it will send out the clock signal, making sure that things are ticking over as they should. Now, in terms of the fetch, decode, execute cycle, in the fetch stage, the control unit fetches the next instruction or the next data item, requesting the address of the instruction or data along the address bus. We saw this earlier. And it does that while sending control signals, such as the clock signal, along the control bus. The instructions data is sent back to the CPU along the data bus, and it's stored in the appropriate register. So that's all happening during the fetch stage. At the decode stage, again, it's the control unit which is at the heart of this. It receives the instruction, it decodes it. It looks it up in its instruction set, it makes sense of that instruction. It now knows how to carry out or execute that instruction. So that's what it does. It executes it. The arithmetic logic unit is where the execution takes place. It's going to perform that appropriate calculation, after which the control unit will use the address bus to request a memory location to store the output. So even after the execution stage, the address bus is still used. It's used to say, hey, main memory or RAM, whereabouts would you like the data to be stored? And then the main memory will say it needs to be at a particular address. And then the data bus is used to actually deliver the data from the CPU back to main memory or to the input-output devices, depending on the situation. Okay, the CPU structure and assembly language. So all von Neumann CPUs, they've got instruction sets. Now an instruction set is simply a list of instructions that the control unit understands, it knows what to do with. And there aren't actually that many instructions that a CPU will need to do or need to deal with or execute. Now here's just a very, very small list of some of those instructions, but these ones are very important, especially when you're trying to write and understand simple assembly language code. So one instruction is add. That's purpose is simply to add things together. That's what the instruction means, to add things together. Sub means subtract numbers from one another. STA means store a value in the accumulator. So that A means accumulator. LDA means load a value from the accumulator. BRA means branch to a different part of the program. And out means output a value, and that's usually the case after processing. So there's a few instructions, and we'll have a look at some of those in action. Now, we said earlier that the CPU has got some registers. It's got some really important registers. They're so important that they've got their own names. Now, registers, remember, are tiny little memory locations, memory stores, and the special ones that you need to know about are the accumulator, and I've sort of mentioned that in the previous slide, the program counter, the memory address register, the current instruction register, or just the instruction register, the memory data register, and we'll have a look at what these specialized registers do over the next few slides. Okay, so here is an example of a program that has been loaded into, well, you can think of it as the RAM, or you can think of it as the memory location in the CPU. So in address 0, we've got the instruction LDA4. In address 1, we've got the instruction sub5. In address 2, we've got the instruction STA6. There's nothing in address 3. And then in address 4 and 5, we've got some data. We've got 5 in address 4, and we got the number 2 in address 5. So the first 3 memory locations have instructions, and address 4 and 5 have data. Now, in terms of these registers, they have a really important part during the fetch, decode, execute cycle to make sure that we can keep track of what cycle we're on and where data is sort of being held when it's retrieved from the RAM, and what the next address needs to be, and so on and so forth. Okay, so during the fetch cycle, the program counter starts off as 0. Now this means that we have, it's the start of the program. So to make things simple, we'll say that the first instruction needs to be retrieved from address 0 because it's right at the start of the program in action. So the program counter, which is to keep track of the fetch, decode, execute cycles, it just counts every cycle. It starts off at 0. We move that 0 into the memory address register. That means that we know that we want to get whatever is stored in address 0 first of all. So the program uses the value in the MAR, in the memory address register, to look up the appropriate instruction by looking in address 0. And what is in address 0? Well, it's the instruction LDA4. So that instruction is then sent back along the data bus, and it is put into the memory data register, into the MDR. So we have now fetched that instruction. Now, because it's an instruction, it is placed into the instruction register, and now the CPU is ready to try and work out exactly what that instruction means. So it needs to decode it. So we're onto the decode stage. So it looks up LDA in its instruction set. There's an error there on the PowerPoint. That should say instruction set, not the character set. The control unit does this job and recognizes LDA4 as meaning load the contents of address 4. So the CPU has now decoded that first instruction and it's ready to execute it. So, execution of that instruction. The instruction says load to the accumulator the contents of address 4. Well, let's have a look. What's in address 4? Well, it's the number 5. So that then is moved into the accumulator. It's transferred from the RAM along the data bus into the accumulator. And that's the first fetch, decode, execute cycle complete. So we're on to the second fetch, decode, execute cycle. So the program counter goes up by 1 because we're on to that second cycle. And now we're ready to go again. Using the program counter to keep track of which addresses we need to be looking in to get through the instructions, the 1 moves to the memory address register, into the MAR. Now the CPU knows that it needs to fetch the contents that is at address 1 in the RAM. So it requests the data by putting that address along the address bus to the RAM. The RAM then will send the instruction back along the data bus into the CPU's memory data register. Because it's an instruction, it is moved into the instruction register, and then it is looked up in the instruction set. Now, it is decoded. The control unit works out what sub 5 means. It recognizes that sub 5 means subtract the contents of address 5 from the accumulator. Not subtract the number 5, but subtract the contents of address 5 from the accumulator. So it's now decoded that instruction. It's ready to execute it. So what the CPU will do is it will indeed subtract the contents of address 5, which if you look in the RAM, in address 5, you've got the value 2. So 2 is subtracted from the 5 that's in the accumulator to leave the value 3. And that's the second fetch, decode, execute cycle complete. Now, if you were to go again onto the third cycle, hopefully you will be able to see that the program counter will become 2. The memory address register will become 2, therefore. It will therefore request the instruction in address 2. the instruction is STA6. That will be sent back along the data bus into the memory data register. Because it's an instruction, it will be put into the instruction register. The CPU will understand, it will decode what that instruction means. It means store the contents of the accumulator into address 6. Once it's decoded that, it will execute it. Now, what's in the accumulator? Well, from the previous cycle, the value 3 is in the accumulator. So if it's to perform STA6, it means store the number 3 into address 6. So the 3 is taken from the accumulator and it is passed back along the data bus, back to the RAM and stored in address 6, just here. Okay, common characteristics of a CPU and how they affect performance. Another typo, terrible. Okay, so there's a number of common characteristics of a CPU, and in your exam you need to know what those characteristics are. You need to know how they affect the performance of a computer. So the clock speed is very, very important. That will obviously affect the speed of how quick a computer can actually perform. So the speed of the fetch, decode, execute cycle is determined by the CPU's clock speed. Now, the CPU's clock is actually a vibrating crystal. It's a crystal that has an electrical current sent through it. It vibrates at a constant rate and therefore allows us to actually have a synchronized situation inside the CPU. So the speed of the clock is measured in hertz, which is the amount of cycles per second, or vibrations per second. A clock speed of 500 hertz means 500 fetch, decode, execute cycles per second. Current computers usually have speeds of about 3 gigahertz, which means 3 billion vibrations or clock cycles per second. So overclocking is something that you can do to a CPU to actually increase the speed of the clock, which means that those fetch, decode, execute cycles will happen faster and therefore the CPU will perform calculations much quicker. So it's possible to increase this clock speed. It's known as overclocking. In theory, if the clock speed is faster, then it can perform more calculations a second. But the problem is that the CPU will get hotter and hotter the more work it has to do. It's going to be designed to work or to run at a safe speed. So if you're going to overclock it, it's probably not going to be able to be working much faster before it overheats and gets too hot. The other thing is that if you overclock a CPU, the rest of the devices, they may not fall into the same synchronization. It's been designed to work at a certain speed. If you get it too quickly, you're probably going to have a few glitches along the way, okay? And the CPU won't be able to perform instructions before the rest of the devices have actually completed what they need to do. And sometimes you're going to get a few issues with programs having errors. So we need to make sure that, if we are going to overclock it, that we make sure that it stays cool and that it's not going to cause any further problems to the performance of a CPU. Okay, the cache. So we've seen that the CPU can work very quickly, 3 billion cycles per second. But the CPU can actually only work when it's supplied with data, and the RAM, which supplies the data, can't actually supply it quick enough. So to overcome this, the CPU's got its own little bit of memory known as the cache, and it won't just copy the instructions needed at that time. It will also copy over some instructions that it might need in the future. And it might also copy some instructions that it knows it's going to need over and over again in the future. So the cache memory has read speeds similar to the CPU. It can therefore deliver instructions to the CPU as quickly as the CPU needs it, unlike the RAM, which cannot maintain or keep up with demand. So to improve efficiencies, the CPU's control unit will first look in the cache for the next instruction to see if it's already been copied, which reduces the time taken to access the data. And if the cache is larger, it's therefore much more likely that the next instruction that it needs will already be transferred from the RAM to the cache, and therefore the CPU can continue to work at a really fast rate. So the larger the cache, the more chance that next instruction is there ready to be executed. So if the data is not in the cache, request it from the RAM. Data and future data is copied to the cache for quicker access. Okay, CPU cores. So CPUs of today, they pretty much at the limit of today's technology in terms of how quickly they can process data. So if CPUs can't go much faster, the solution is to add maybe 2 CPU cores together, or 4 or 8 and so on. So that although they can't go faster, they can actually fetch 2 instructions at the same time, decode them at the same time, and execute them at the same time, in theory. Okay, not all programs are designed to allow for this, but certainly it can cause some or produce some good benefits. So these chips are called cores, and because the various cores can each carry out their own fetch, decode, execute cycle, it means that instructions can be processed at the same time. So allowing a CPU to process more data during the same time period. Doesn't mean it's actually executing a piece of data faster, but it can process more data during the same period of time. Now a dual core processor will have 2 cores, a quad core will have 4, pentacore has 5, octa-core has 10, and decacore has 10. Octa-core has 8, and decacore has 10 cores. So there are 2 ways in which a CPU with more than 1 core can process more instructions in the same time period. They can carry out parallel processing, which is when the same program can have 2 instructions processed at the same time. So the same program, 2 instructions processed at the same time. More cores also enables multitasking, where each core can process 2 different programs' instructions at the same time. So there's 2 different ways that more cores can benefit the performance of a computer. Parallel processing, 1 program having its instructions fetched, decoded, and executed at the same time, and more cores meaning or multitasking, sorry, which is where different programs can have their instructions processed at the same time. Either way, more cores means that more instructions being processed at once, which can improve performance. However, it doesn't necessarily mean CPUs work faster, as some programs do not allow more than 1 instruction to be processed at once, so please be aware of that when you're answering your exam questions on it. Okay, pipelining. So pipelining is where the output of one stage is the input of the next, and pipelining is a really important computational method to speed up tasks being carried out, and the CPU uses pipelining really well. Now, just to understand what pipelining actually is in a different setting, if you think about the processing of washing and drying 4 sets of laundry, we could have this scenario. We could be washing our first set at 10 AM, an hour later we could then be drying that set, and when that set of washing is done, we could move on to the next set of washing. We could wash it for an hour, dry it for an hour. We could then go on to the 3rd set, wash it for an hour, dry it for an hour, and then we can go on to the 4th set. We could wash it for an hour, dry it for an hour. Now that is all very well and good. It takes 8 hours to complete 4 sets of laundry. But actually, if you think about it, there's going to be a time where after you've washed the first set and you're on to drying that first set, the washing machine isn't in use. Now that isn't very efficient at all. So if we were to implement the idea of pipelining, we can actually wash the second lot whilst drying the first lot. And that can reduce the time it takes to process these 4 sets of washing. Now the CPU does a similar thing, and we'll go on to that in a while. But just to go back to this scenario, you can see here that if we were to actually use the principles of pipelining, we could be washing set 2 whilst drying set 1, washing set 3 whilst drying set 2, washing set 4 whilst drying set 3. In this example, queuing up jobs as separate pipelines reduces the time the entire process down to 5 hours. Pipelining is therefore a really important computational method, and as I said, the CPU does this. So pipelining has many uses in computer systems, but in the CPU, what it does is the CPU, as one instruction is being executed, the next can be decoded and the next can be fetched. And in this way, instructions can be queued up, reducing processing time. So think about those 3 stages. It's fetched an instruction, it's decoded it, it's executed. Whilst it's executing it, it could be decoding another. So again, to say we fetched the first instruction, we decode the first instruction. Whilst that first instruction is being decoded, we can fetch the second instruction. Once that first instruction's decoded, it will move on to the execution stage. So whilst that first instruction is executed, the second one can be decoded, and then we can fetch the third instruction. So by using pipelining, we can reduce the processing time considerably. Now, pipelining does have limitations. It only works if the CPU knows what instruction needs to be fetched next. If it fails to correctly forecast that next instruction and as a result fetches the wrong instruction, the entire pipeline has to be flushed, cancelling out any benefit that pipelining gave in that round of cycles.